Welcome to Plutus STEM, and today we are covering the concept of ideal and non-ideal solution. Okay, from the past few classes we are talking about organic chemistry, inorganic chemistry, and today we are focusing on physical chemistry. So the thing is, in physical chemistry for class 12th, there's a chapter, that unit you have, that is called as your solution. In solution, we particularly start with the concept ideal and non-ideal solutions we have. So ideal and non-ideal solutions. Now, what are ideal? In this class we'll be focusing on what are ideal solution, how they are formed, why we are talking about them, why do they exist. Those are the prime question for which we are seeking answers today. So the first one being ideal solution. Ideal solution. Now, theoretically, these are those solutions in which the solute and solvent solute interactions are similar to solute solvent, the solute and solvent interactions are similar to solute solvent interactions. Okay, for solutes from here on outwards I'll be using B, and for solvents I'll be using A. So here the AB forces that are existing between the solute and solvent are similar to solute solvent and solute interactions. Second one being that when the two solutes and solutes are mixed, there will be no change in enthalpy of the mixture. That means no amount of heat being evolved or being absorbed throughout this, and the change in volume will also remain zero. Now, what does it mean? So for example, if I make up a beaker, in this beaker there are some solvents that are present of A types, and then I add some solute of the type B. Now, when this happens, that means the bonds that are existing between these species, they are of exact same type. That means if this bond is ionic, the other one will also be ionic. If in the solute, if this one is covalent, then in solvent the bonds will also be covalent in nature. So why we are emphasizing that the bonds in both the cases should be same? It's because when they are interacting with one another, it is the bond that will be of uttermost importance to us, because when an electrolyte is being added to a solvent, the bonds are either getting formed or being broken. But when they are completely same, or there's a very less difference between them, then the bond formation and bond breaking will not result in any absorption or any evolution of energy in any form, which makes up an account for why ideal solutions have no enthalpy change with respect to them. Okay, because even if I break these bonds and the solute and solvent will start to interact with one another, I can still say since the bonds are exactly same, there is nothing new that has been formed, and the solutes and solvent will be interacting by the same forces with one another. This is what we mean by ideal solution, and the prime examples of ideal solutions exist for those species that have same type of forces with respect to one another. For example, benzene plus CCl4, both are non-polar in nature, so when they are dissolved together there are no bond formation or bond breaking in this solution, so that's why there will be no enthalpy change and hence this will be an ideal solution. So the ideal solutions are primarily those that obey Raoult's law. Raoult's law under all conditions of temperature and pressure. Under all conditions of temperature and pressure. Temperature and pressure. Next, moving on to non-ideal solutions. So, non-ideal solutions are those in which the solvent and solute forces can either be greater than or lesser than. It can be greater or even lesser than, greater than or even lesser than the solute-solute and solvent-solvent forces. And solvent forces. So that means either they will be held more strongly than their original molecules or they will be less closely held, because of which there will be a difference in their properties. That means some bonds will either be broken or some new interaction will form, because of which there will be exchange of energy, and in these cases the enthalpy change will always have some value but will never be equals to 0. Similarly, since heat is being evolved or absorbed, there will be change in volume because the solvent will expand or some of it will lose from the solution. Next, that these are those solutions, these are those solutions which do not obey Raoult's law, do not obey Raoult's law. So, what is happening in them? For example, this usually accounts for when you are having different types of solute type or different types of bonds behavior. For example, if I have taken a non-polar molecule, sorry, a non-polar solvent with a polar molecule, let's say alcohol or let's say some other molecules which can exist as a charged species. For example, B minus. Now, this P minus, since it cannot interact with the solvent, their difference in properties will make up for it. That means here it will start interacting with the other species that it has made in the solution, which can either be either positive charge or negative charge species. For example, if you are taking alcohol, alcohol can exist as alkoxide ion and removing H plus ion. So since they cannot interact with the solvent, they will start interacting with themselves much stronger. So, in case of solvent, what will happen? If you are taking solvent which are in different properties, for example, if you are taking benzene, in benzene type of molecule, since the benzene contains pi electron density, that means this is also negative charge. So this negative charge can interact with the positive charges of the electrolyte and can establish new bond with itself, which can lead to this increased interaction will separate the solute from its counterpart, thereby creating more separate charge entities. Although alcohols has some polar character, but still they are primarily your non-polar compounds. So based on this new interaction can increase interaction between the solvent, interaction between solute and solvent. Or in other ways, if it is transferring its charge density to itself, this species can counteractively can combine back its solvent molecule, and hence the interaction can also be decreased. Now, it entirely depends on which type of solution you are working with, so the interaction can increase or decrease, which later stems into two different cases: solutions of positive deviation, in which the interactions are decreased and you are receiving more vapor pressure than the normal case, or you are having negative deviation, in which the interaction was so strong that the vapor pressure of the solution was decreased. So this is the whole concept regarding your ideal and non-ideal solution. So I hope you have understood it. You have cleared some doubt why we are studying ideal solution, how they are formed, which conditions are required in them, and what kind of forces that are working behind them, giving us two different variations, and how those different variation later circulates into other variations. So that's it from my side for today. In the next class, we'll cover about the positive and negative deviation with specific examples, and how the interaction between different types of molecules, solute and solvent, affects the vapor pressure of the solution. So till then, keep watching, like, share and subscribe. And in case of any doubts, you can add it to the comment section and we'll get back to you. Thank you for joining us for today.